At over 70,000 screws per minute, one overloaded belt is enough to stall the entire factory. Not because the ratios are wrong or because the machines can't keep up, but because throughput logistics break down. Most Satisfactory players blame the screws when their systems collapse. In reality, screw production often exposes weak planning and system logistics, even in my own builds. Instead of eliminating them with alternate recipes as so many players do, I decided to scale them and build a screw factory that is designed to produce 70,200 screws per minute to see if I could get the logistics to work out. And I nearly failed for one simple reason. Even the best Mark 6 belts in the game cap at 1,200 items per minute. At over 70,000 items per minute, throughput design becomes the single most important decision in a build like this. I decided to break the factory into 3 separate production lines. Without that type of separation, the design would fail before it even ramps up. I'll come back to why that zoning decision was critical near the end of the video. As I started designing, I saw that the highest impact initial risk wasn't the final screw production. It was ensuring the stability of the raw material inputs. This system consumes 3,600 iron ore per minute and 3,600 coal per minute. The iron arrives cleanly on 3 dedicated 1,200 per minute belts. That part is simple and controlled. Coal's a different story. It's delivered to the factory by drones from 4 distant mines. Drone logistics introduce variability. If coal throughput dips, steel production fluctuates. If steel fluctuates, screw output destabilizes. Before any belts were placed on the factory floor, I added additional drone ports at 2 of the mine locations for added insurance. Supply had to exceed demand, and that redundancy prevents machine starvation before it even begins. Primary processing comes next in order of impact. Iron ingots are produced in 3 separate smelting blocks, each capped at 1,200 per minute to match a single Mark 6 belt. Centralizing them would have overloaded output lanes almost immediately. The risk here is simple. If one belt saturates, the entire downstream chain starves, and the target output becomes mathematically impossible. Using 3 smelting units solved that issue. Secondary production introduced another logistical constraint, steel ingots at 5,400 per minute, which are then converted into 1,350 steel beams. At this stage, the main issue isn't machine count, it's material distribution. All of the belts and manifolds used here were carefully designed and installed to allow each production step to feed in a forward direction in dedicated lanes to avoid congestion and maximize throughput. Through this design and build process, belt congestion was the true silent killer. At over 70,000 screws per minute, I had to use 3 vertical layers of Mark 6 belts in each lane of the output stage. Any miscalculation in routing would instantly cascade back through the system. That actually happened during one of my early tests, where the system stabilized, but at the wrong number. I initially underestimated the routing complexity between steel beams and final screw constructors. One overloaded belt line and things came grinding to a halt. It wasn't by much, but it was enough to miss the design goal. I just needed to split belts cleanly by zone and I was back up and running. There is no storage system in place yet, and the final output from all 3 of the production lines feeds directly into 72 awesome sinks. I did that during the build process to eliminate any back pressure from the system so that I could observe the pure flow of the production lines. Future rerouting of these screws to a different factory would be very easy to do. When I turned this factory on, I watched the belts fill, the constructors engage, and the 3 vertical lanes saturate with thousands of screws. But to me, the most surprising part about this build isn't the pure output volume of screws, it's the overall stability of the factory. And this really only works because of the production zoning being tied directly to the Mark 6 belt capacity. Thankfully, I was able to use tools like Satisfactory Modeler to plan this out and think through the logistics before I even loaded into the game. When belt capacity is understood and zones are planned around it, even the most disliked item in the game becomes predictable, stable, and scalable. If this helped you, make sure to hit the like button, subscribe to the channel, and check out my other great Satisfactory videos right here. See you on the next one.